Electrical conductivity measurements of thin films. We will cover the Wheatstone bridge method, the 4-probe method, and the Van der Poel method of conductivity measurements. Wheatstone bridge method. In this method, the thin film whose conductivity is to be measured is connected in one of the arms of a Wheatstone bridge. There is a source which produces evaporations and whose rate of deposition on the thin film could be controlled using a shutter that is connected to a driver and a relay. Using this method, resistance of metal films can be very easily measured by placing the film in one of the arms of a DC or AC Wheatstone bridge. For a given value of the ratio arms of the bridge, the film resistance is proportional to the variable resistance R, which can be measured by automatically recording the potential across it. Several variations of the bridge circuit can be employed for recording the resistance changes from several mega ohms to a fraction of an ohm by automatically changing the value of the ratio arms. The variable resistance R may be set to a value corresponding to a certain film thickness. When the bridge is balanced, a relay may be energized to actuate a magnetically controlled shutter to interrupt the vapor beam and then shut off power to the vapor source. Using a sensitive DC amplifier, resistance changes of approximately 0.01% can be measured. The second technique is the 4-probe method. It is the most common technique that is used to measure the resistivity in semiconductors or thin films. The setup consists of 4-point collinear probes where a constant current is applied in the outer probes and the voltage drop is measured in the inner probes. The probes are separated by a distance S and the thickness of the film is T. The sheet resistivity can be calculated to be ρ equal to V by I times CF, where CF is the correction factor based on the ratio of the probe to wafer diameter and on the ratio of wafer thickness T to the probe separation S. If the sample is of semi-infinite volume and the inter-probe spacing are S1 equal to S2 equal to S3 equal to S, then it can be shown that the resistivity of a semi-infinite volume is given by ρ equal to 2 pi S times V by I. Because the samples are of finite size, Valdez calculated the correction factor for 6 different boundary configurations. He concluded that if the distance from any probe to the nearest boundary is at least 5 times S, no correction factor is required. Therefore, for sample thickness equal to or lower to 5S, the resistivity is calculated as ρ equal to A times 2 pi S times V by I, where A is the thickness correction factor. This figure shows a plot between T over S and the correction factor A. From this plot, it can be observed that for T over S greater than or equal to 5, A equal to 1, and T over S less than or equal to 0.5, the curve behaves as a straight line. Thus, A can be obtained by calculating the slope. Hence, for samples of thickness equal to or less than 1/2 the probe spacing, A could be calculated to be 1 by 2 natural logarithm of 2 times T by S. When this value is introduced, the resistivity becomes rho equal to pi t over natural logarithm of 2 times t by s, where t by s is less than or equal to 0.5. Finally, dividing both sides by t, we get the sheet resistivity as rho s equal to pi over natural logarithm of 2 times t by s, where t by s is less than or equal to 0.5. It should be noted that s is independent of the sample geometry and that s only depends on the studied material. The third method is the van der Pol method. This technique was invented by van der Pol and is extensively employed in semiconductor industry for determination of resistivity of uniform samples. This technique requires an arbitrarily shaped thin plate sample having 4 very small ohmic contacts placed on the periphery, usually at the corners of the plate. The figures on the left shows a schematic arrangement of a typical van der Pol experiment. There are 4 conditions that must be satisfied to use this technique. In the first, the sample must have a flat shape of uniform thickness. Second, the sample must be homogeneous and isotropic. Third, all 4 contacts must be located at the edges of the sample. In order to determine the resistivity of a uniform sample, the sheet resistance Rs needs to be determined. As demonstrated by van der Pol, 2 characteristic resistances Ra and Rb are associated with the corresponding terminals as depicted in the figure. To determine Ra, a DC current I is applied across contact 1 and contact 2, and the voltage V43 is measured across contact 4 and contact 3. Then Ra equal to V43 over I12. To determine Rb, a DC current I is applied across contact 2 and 3, and the voltage V14 is measured across contact 1 and contact 4. Then Rb equal to V14 over I23. These characteristic resistances Ra and Rb are related to the sheet resistance Rs through the van der Pol equation as exponential minus pi Ra over Rs plus exponential minus pi Rb over Rs equal to 1. This equation has to be solved to get Rs. Then the bulk resistivity ρ is obtained from Rs as ρ equal to Rs times T, where T is the thickness of the film.